Okay, let's continue. Before doing that, I would like to show you what Phil Rowe looks like. Here is a recent picture by him, because he received this year the AI Fluid Award, which is the American Institute of Aeronautics and Astronautics. So it's a prestigious reward. And there he gave, on this occasion, he gave an interesting lecture on the history of CFD. So if you want to follow that, I think I put this link on its learning, so you can look at it. It's, I think, around 1 hour. And it covers the history of computational fluid dynamics by one of its best people. Okay, so we continue by looking at another method that is, as I told you before the break, much simpler, but not quite as good as the upward method. But it is useful to know, because in some occasions it is good to get a solution and where you don't have to worry of implementing an entropy fix, and so that is simply easier. And that is the Lax-Riddichs method. So that is simple and robust. So that is simple, robust. So you don't have to change anything if you get results. But the results might be really sometimes almost useless, because they are very dissipative. And especially for delta t to 0. And the flux function is the following. So the numerical, so the Lax-Riddichs numerical flux is the following. That is 32. We have again, we consider here, because it's that is convenient, just the phase j plus 1/2. And then we do the acronym LF for Lax-Riddichs. And then we start again, as we have done also for the upwind method, with the average of the flux function in the cell J, and the average in the cell J plus 1. So that would be the central finite volume method, but that we don't want, because it is conditionally unstable with the explicit Euler method in time. And now the catch is that the numerical viscosity term that is here appearing, it's not directly numerical viscosity, but the coefficient in front of the derivative of the difference in uj plus 1 uj is simply delta x over delta t. So we have this form. So extremely simple. You see here, before we had there the modulus of uj plus uj plus 1/2, which we had to replace by the q of this expression if we want to use Harton's entropy fix. But here it is simply delta x over delta t. So the dimension is the same, it's the dimension of velocity, but it's just the grid spacing divided by the time step size. And there you see why we get a problem when delta t goes to 0, because the numerical viscosity is then divided by delta x, multiplied by delta x, so we get delta x squared divided by 2 delta t. If delta t goes to 0, the numerical viscosity goes to infinity. So we get a completely viscous flow in that case, which does not represent the reality of inviscid flow at all. So that's a problem. Nevertheless, the method is first order in time and space, when we use the explicit Euler method in time. So the accuracy is the same formally, but when we apply it, we will see differences. the method is stable and total variation diminishing under the same CFL condition that we saw for the upwind method. That was 21. So you can use it, but you should be very careful with it when, especially when you have small delta t. So a method that is considerably better than this, it's not, it gets close then to the upwind method. That is the following. That is called the local Lex-Friedrichs method. The local Lex-Friedrichs method. Or, so that is what it's called, say, in the US, but in Russia it would be called the Ruzanov method, because it was originally due to Ruzanov, the Russian scientist. And there we use a similar expression as here. So that would be then, if we would give it a number, it would be 33. We would have the flux function j plus 1/2. The local Lex-Friedrichs would then be similar, as we have the same pattern as we have been using all the time. The average of the fluxes evaluated with the approximation to the cell j and j plus 1. But then we would have here an aj plus 1/2. That is, it looks similar as to what we had for the upwind method, but this has a different expression. So it is minus uj, and that is important how we determine this characteristic speed. That is the maximum of the f prime, that is the characteristic speed evaluated in the cell j, and the characteristics, absolute value of the characteristic speed evaluated in the cell j plus 1. So for the Invisit-Burgers equation, this would simply mean that we take here the maximum of uj, modulus of uj, and the modulus of uj plus 1. And the one that is largest, we take them as the value that we use here. So that is then the Ruzanov method, or also called local Lex-Friedrichs. That, you see, does not suffer from the problem when delta t goes to 0, because delta t is not involved here. We have only the characteristic speed involved, and that is independent of delta t. So that is much better. And it is also quite simple. So then we have actually then here two methods: the standard Lex-Friedrichs, where you have to be careful, and the Ruzanov, or also called the Lex-Friedrichs method. Then there is another method that I want you to have a look yourself in the lecture notes or the book, which is a useful method for problems without discontinuity. So if you have a discontinuity, the method that I shall mention now is not useful. But if you have a smooth problem, then it is. So that is the Lex-Wendroff method. We have that also for the Lennard-Action equation. So we can also derive it for one-dimensional conservation law. So I read lecture notes and text. It has a nice idea because it is based on the Fourier expansion in time, and then it uses essentially the same trick that we use with the modified equation method to replace the time derivatives by space derivatives. And then the space derivatives are discretized by central differences, and then we get second order in space and time. So that is the good thing, but the bad thing is it is not TDD. So therefore it is not useful for discontinuities. So instead, I would like to jump to the problem that we get when we have a viscous problem. So far, we have been discussing only inviscid problems. For example, the Burgers equation is just we have just a hyperbolic system, nonlinear transport, but there is no viscous effects involved. So to get those, you have to know how to discretize a diffusive flux. So that is the chapter that we need when we want to solve actually the Burgers equation itself, because the Burgers equation itself contains a viscous term. Kinematic viscosity times second derivative of u with respect to x. So we consider now, and then the character of the equation changes. It is then no longer a hyperbolic but a parabolic. The parabolic, the scalar 1D conservation law. Conservation law of this kind. Let's see if we jump here in the notation. It would be 34. So we have again our control volume, say control volume J from xj minus 1/2 to xj plus 1/2. We integrate the u, which is dependent on x and t. We integrate that over x. And we have fluxes. We have a flux f of u. And that is actually at xj plus 1/2 t. So that is the flux at the eastern phase minus the flux at the western phase, u of xj minus 1/2 t. So that is what we have been discussing all the time. So these fluxes we have been discussing all the time, how to do this discretization of that. But now we add something on the right-hand side, and that is then describing viscous effects.
Question?
Yes?
Are you like differentiating the
Oh, sorry, that was a misprint. Sorry, thank you for that. It is t, of course. Thank you. Time derivative, yeah, right. So it's simply the original equation that we have been discussing so far in integral form. So we have our control volume. So for cell J with these boundaries, we integrate over space, and then we have to evaluate the fluxes, and that is the problem. We have to evaluate the fluxes with the exact solution at the right phase and at the left phase. So far we had that to 0. Now we have the viscous fluxes here. So we have the nu, and we have the du dx, and also in this form. Then we have this at xj plus 1/2 t. So that is the viscous flux at the phase j plus 1/2. Then we have a viscous flux also at the phase xj minus 1/2 t. So that is then coming in addition to what we have been discussing in this chapter 5. So the right-hand side of this equation is then what we need to know. In here, we assume now that the nu is greater than 0, that is appearing here, and that is the kinematic viscosity coefficient. Kinematic viscosity coefficient. And what we discussed with the inviscid Burgers equation, then the nu was 0. So the differential conservative form would be that is then 5, that we have the UDT plus the space derivative of the flux function f of u, that is appearing here, f of u. And on the right hand side, if we would then use then the basic theorem of calculus that we also used here, to get that as an integral over the f dx, we get this here as the integral over d dx of this expression. So then we get here then the d dx of mu du dx. And if mu is constant, we can write it in front. So that would be then the differential form of a conservative form of a parabolic conservation law. And the classical example for such a conservation law, parabolic conservation law, is then the Berger's equation. Classical example is Berger's equation. Before we have discussed the inviscid Berger's equation. Now comes the, say, so to speak, the true Berger's equation. And that is the following. 36. We have the time derivative of u, which comes from the velocity. And then we have the space derivative of u squared half. And on the right hand side, we have now the new constant. We have the second derivative of u with respect to x. So that is the Berger's. So and here nu is constant and nu is positive. If nu is 0, we have the inviscid Berger's equation. So then we do the finite volume discretization of this general equation, and we do that then in the same way for the fluxes as we did for the scalar hyperbolic conservation laws that we have discussed. So that is just the same. The only thing that we have to decide on how to do this discretization. So then we get the finite volume method for approximating equation 34, and that will then be following. We will use again cell averages, and then the cell average will be entered here in the cell J that we are considering. It will be then the time derivative of the cell average in cell J. And then we will do approximations of these fluxes in the same way as we discussed before. We just call it here fj plus 1/2 minus fj minus 1/2. And on the right hand side we have then to do the discretization of this. And what we do here then is we use the same discretization as we used for the heat equation. So here we have, if you think of it, for the heat equation we did not have this. We had the temperature instead of U, and this was the thermal diffusivity. Otherwise we had just this. So what did we do? We had the nu, and then we had here the discretization here will be the uj plus 1 minus the uj divided by the xj plus 1 minus xj. That will be that discretization. And the discretization of the j, this one here, that will be then involving the neighbors. That will be j and j minus 1. So that is then the central discretization. So minus mu uj minus uj minus 1 divided by xj minus xj minus 1. So that will be then the discretization. That means we use a central discretization for the diffusive flux. And if we are away from the boundary, then at the boundary we have to do similar treatment as we discussed for the heat equation near the boundary. But if we are away and we would have delta x constant, we can simplify these expressions. So that is in here, fj plus 1/2 is a numerical flux function for the inviscid turbidity, so that we have already discussed. For example, we could use the upwind method, or we could use Lax-Friedrichs, or we could even use Godunov method. It would also be an option. So where that is used and what we have used, we have central discretization for the diffusive flux. For the diffusive flux, like for the heat equation. Just the same. So what can we say about, and then the time discretization, we decide again on what we like. If we like explicit Euler method, or if we like other time discretizations, we can do that, because then we decide on how to do that. But the discretization of the diffusive fluxes itself by central discretization is in general okay. So we can say that the central diffusive flux when we use the central discretization is in general giving us good results. Usually okay. And we have in general just this discretization itself, only the central diffusive flux is second order for a smooth grid. For example, if we have an equidistant grid, then we can show that by Taylor expansions. However, the disadvantage is that this method might lose consistency if the grid is non-smooth. So that is a disadvantage of this approximation. So one has to be careful. That is always the advice. When you vary the grid spacing, vary them smoothly. Otherwise, you might get a problem. So the minus that I want to write now, that is belonging to this central diffusive flux. So the negative consistency may be lost for non-smooth grid. Then you are approximating something that you don't want to approximate. But in general, these discretization of these diffusive fluxes are not a problem. The challenges are usually the discretization of the inviscid fluxes, these non-linear fluxes. Okay, so then we have an overview over that. And what we have now discussed, and that was the focus, was how to discretize these fluxes for the 1D hyperbolic conservation. So these fluxes. And the ones that we found useful were the TVD ones, the total variation diminishing ones. So the Godunov method is useful, the upwind method, Lax-Friedrichs, local Lax-Friedrichs. Lax-Wendrod is not useful because it is not TVD. And the one that I mentioned, but what we did not discuss in detail, is the Enquist-Osher method. So they are useful methods, they are all TVD. But they have one thing in common, they are only first order, only order delta x. So the goal, what we want to follow now, to turn to now, is to get these methods to higher order. And there is a trick to do that, and this trick is actually due to a colleague of Tilrow, Bram van Leer. He's also at the University of Michigan. He comes originally from the University of Leiden in the Netherlands. He's actually from the beginning astronomer. You have star collisions, you have shocks, so you have then also such hyperbolic problems, and Bram van Leer figured out a way to get these methods higher order by a relatively simple trick. So that brings us now to the next chapter, chapter 6, where we look at higher order finite volume methods. So, the goal is to get so-called high resolution methods that are at least second order in smooth flow and which do not have oscillations at discontinuities. So, and we shall focus on higher order TVD methods. TVD, total variation diminishing. So by this property we can avoid the Gibbs phenomenon of oscillations near discontinuities. So what we do is first order TVD methods. We state that here. Like Godunov, upwind, Lax-Friedrichs, local Lax-Friedrichs, Enquist-Osher, and so on. They can be extended to second order I add already except for extrema, so there where you have a maximum or a minimum of u, by what we are going to learn now is Van Leer's so-called MUSCL approach. So when you invent a new method, you have also to get a good name for that. And Bram van Leer chose MUSCL to mean monotone, upwind centered, schemes for conservation laws. So that is what the name means. And the idea is, so in finite volume method, the cell average approximation that we are computing in the finite volume method. So average approximation uj. That is what we usually do. We compute a value in a cell which is approximating then the mean in the cell or the cell average. That is not, and here the name is introduced, reconstructed. So we shall understand that in a minute. As constant in a cell. For example, that is what we have been doing. We have assumed, and that is the basis of Godunov's method, we have been assuming that the distribution inside the cell J is simply uj itself. That was what we have always silently been assuming with the Godunov method. So that we have simply, we are using these averages in the whole cell. That is from xj minus 1/2 to xj plus 1/2. So that is what we were doing when we looked at the cell. We have x, and we have, if we have here the u, then we had, and we have here xj minus 1/2, and we have here xj plus 1/2. So that is then the cell. We have the midpoint here, then that is where we plot the solution, but it's in fact just an average that we plot. If that is then our uj, we were assuming for doing the Godunov method that this is constant. That was what we have always done. Because we had said, we were saying, when we solved the Riemann problem, we assumed that the value of u of x as a function is like that. So we were assuming that it is constant in each cell. uj plus 1 constant in the neighboring cell, and so on. We were always assuming that the distribution is constant. So reconstruction means that the value is that we have the average. From that we get how the function looks like. So we get from the average, we get something, the knowledge over how u looks into as a function of x inside the cell. And the simplest way is to assume constant. That is what Godunov has been using. But what Samir has been using was he has assumed that it is linear. So then we can get it. We can get a better approximation. So in that sense, then he was assuming, okay, we still take the uj, but we take now also the slope into account. That we have to determine in some way. The uj prime. So uj prime is now supposed to be an approximation of the slope. So uj prime is supposed to be an approximation of du of xjt dx. So what will that look like? For example, if you have this example here, we could have a distribution maybe like that. So that we have a linear distribution. But we do it in such a way that the average that we have for the linear distribution is the same as the average for the constant distribution. So that means we do it such, note that 1 over delta x integral from xj minus 1/2 to xj plus 1/2. When we do this integration of this linear form, u of x dx, that is equal to uj. So we do not change the cell average. That is the point. So we keep the averages untouched, but we get better approximations inside the cells. If we have better approximations inside the cells, we get also better approximations at the endpoints to define the Riemann profiles. Okay, so we'll continue on that next week, and we'll see that the form that we get in the end is relatively simple, but we need more points. To get the slopes, we need not only the next neighbors, j minus 1 and j plus 1, but we need j minus 2 and j plus 1. Okay, so tomorrow from 6 to 8 in the evening, another guidance hour, and then on Monday, feedback on exercise 3. So please remember the deadline for exercise 3 is on Friday, and some teaching assistants would like to have that by 13:15 because he would like to do the correction on Friday afternoon.